Good morning to everyone. Today we are here to present our major project titled A Novel Intelligent Traffic Recovery Model for Emergency Vehicles based on machine learning. Myself Abhinav, VTU 20050. So our presentation will cover the main following key areas like the main motivation behind our project in the introduction, a review of the existing systems in our literature review, an overview of our proposed system, and also methodology architecture which we have used, an algorithm with a detailed description, implementation, testing and validations, and mainly result and analysis. So coming to the introduction, in urban areas like environments, efficient passage for emergency vehicles like ambulance and fire trucks is critical. Delays caused by traffic management or traffic congestion can have severe life threatening chances. So to optimize the traffic flow during the emergencies while maintaining overall traffic efficiency, we are using a pygame based simulation. The system demonstrates how machine learning can significantly improve emergency response times without disturbing normal traffic patterns. The main motivation stems from recognizing the critical importance of emergency vehicle responses in urban settings where congestion increases public safety. So the traditional traffic management system lacks in the intelligent need, like in smartly recognizing the emergency vehicles in the lanes in urban dynamic environments with growing population and increasing vehicle counts. So there is an urgent need for smart systems that can create efficient pathways for emergency vehicles while maintaining the general traffic flow. So our main primary objective was to design and implement a novel intelligent traffic recovery model that leverages machine learning to prioritize emergency vehicles and efficiently restore the traffic flow towards afterwards. So basically, uh, project main aims to solve or improve the critical problem of delayed emergency response times in congested environments. Number one is emergency vehicle response times. By this project, we have reduced the response times by 30 to 40 percentage compared to conventional traffic systems like traditional traffic system. And the second one is traffic flow during emergencies. We are maintaining overall traffic efficiency by prioritizing emergency vehicles and also by avoiding the cascading congestion issues typically caused by emergency vehicle passages. And the third one is adaptive management. uh,
From this, I am going to continue the presentation. Myself, Rashekar, and from the literature review, we looked at what other people have done to solve problem, and some of the limitations that we have looked over this, like not very good getting traffic back, and our research showed that we need a smarter way to handle this. These are some of the literature reviews that we have taken into consideration, and these are others. And our idea is new smart traffic system that uses our system like real-time traffic information, and which is used by machine learning to not only give emergency vehicles a green light but also learn from the traffic patterns and make the traffic flow better and afterwards. Okay, let's continue with the methodology now. Mm, in methodology, we have adapted V model development approach for this project, and this allowed us to maintain a strong validation process for each development phase. And the first step was we have gathered all the required uh, data, and we defined the core traffic rules specified for the emergency vehicles and the prioritization, set a clear performance criteria, and we have planned a system architecture. Let's see our system architecture. uh, the simulation was developed using pygame where we design realistic road networks and intersections. The traffic system module manages multi-core traffic operations, and here we have used the queue learning agent. It maintains a queue table to learn optimal traffic signal control, and updates is based on the reward feedback from the traffic flow. And the decision making module that executes the real time signal changes and give the priority to the emergency vehicles whenever it is necessary. And then the performance metrics, to evaluate the system performance, we integrated real time traffic flow monitoring, directional traffic load analysis, and overall efficiency measures of the signal control decisions.
Myself Singham Kishan, and I am going to continue with the algorithm with the description. The intelligent traffic recovery model uses q-learning and model free reinforcement learning algorithm to optimize the traffic signal control for the emergency vehicle. This algorithm learns optimal action policies through experience without requiring a model for the environment. The q-learning algorithm maintains a queue table that maps a state action pairs to expected rewards. For our traffic management system, states represents traffic conditions, particularly vehicle density and emergency vehicle presence, while actions corresponding to traffic signal control decisions. Now, we are going in a detailed explanation of mathematical formation. It is used for the adaptive learning rate, adjust how quickly the agent learns over the time, and it also states that current traffic condition, example vehicle destiny on each lane. Now the implementation details. It includes data execution, data pre-processing. In data execution, we are going with simulation data source. Pygame based traffic simulation generates realistic traffic scenarios. In data collection, real-time traffic tracking of vehicle positions, speeds, traffic signal states, and emergency vehicle status. Data format: structured Python objects for vehicles and traffic signals with attributes for position, speed, direction, and status. And comes to the storage in a memory data structures during simulation with optimal CSV export for analysis. Sampling rate: continuous data collection at a 60 frame per second with state snapshots every second. And I'm going to continue with data pre-processing. It includes state representation, normalization, feature engineering tools to be used in it, and dimension reduction. And coming to the testing and validation process, testing methodology includes simulation testing and component testing. Simulation testing in the sense comprehensive testing in a controlled Pygame environment with predefined traffic scenarios. Component testing includes individual model validation for each system component. Simulation environment, visual verification and frame rate stability. Traffic components, vehicle movement, accuracy and collision deterrence. Q-learning agent, learning convergence and policy consistency. Decision making, response time to emergency vehicles, performance matrices, accuracy of data collection and analysis. Integration testing, verified interactions between all 5 system modules. Stress testing, evaluated system performance under high traffic density. Emergency scenario testing, specific tests for multiple emergency vehicle handling. Tools used: Python, Unitest framework, custom performance monitoring scripts. Here comes under model accuracy analysis, Q-learning convergence 94.7, policy stability after convergence 8.5, average reward out of theoretical maximum 10, decision accuracy 92%, correct prioritization for emergency vehicles 80% for overall throughput accuracy. Significance per project: the 80% throughput accuracy demonstrates effective traffic management. The 37.8% improvement in emergency response time represent potential life-saving optimization. Real world implication: project to reduce emergency response times over 1/3, maintain general traffic flow efficiency while prioritization. Here comes under performance metrics table, metric value, benchmark improvement, emergency vehicle response time 28 seconds, benchmark 45 seconds, improvement 37.8%, system throughput 80.0% value, 65.0% benchmark, 23.1% improvement, mean flow rate 4.0 vehicles per second value, 3.2 vehicles per second benchmark, and 25% improvement. Signal timing optimization 87.5% value, 70.0% benchmark, 25% improvement. Detection to action time 1.2 seconds values, 3.5 second benchmark, and 65.7% improvement. There the pie chart shows the value of traffic flow directional distribution. Continue with the demonstration in the VS Code. This is our the project code, comes under the stimulation, which the output get here comes our stimulation output.